All right. Good morning, everybody. Welcome back. So let's start a new week in our class. So let me tell you one thing before we start. So I understand that this course has a lot of things that you have to learn in a sort of a fast way. So that will require you to work a lot of hours extra class. However, doesn't mean that it is impossible to do it. Okay, so it will require a lot of work, but I'm sure we can do it. You guys are doing a very good job so far. So let's keep on track. And when you see the semester will be already gone. Okay, so for today, I would like to finish what I need to talk about redox reactions, and maybe we can start the next chapter. So let me go back here. Let's just start with some quick announcements here. You have online homework, chapter 4, part 2, due on Friday. And for this week, we will not have in-class assignment, sorry. Therefore, we will meet here on Friday for a regular lecture. All right. So on Wednesday, I started to discuss with you about oxidation number. So remember that the oxidation number, or also called oxidation state for a given element, gives us an idea of how many electrons this element lost or gained when combined with another element or when isolated. A negative oxidation number means that electrons were gained. Therefore, we have excess of negative charges. And the opposite, and a positive oxidation number, means that electrons were lost and we have an excess of positive charges. And I show you a set of 6 rules. And with those rules, we can calculate the oxidation number for any kind of element in any kind of compound. So what was left here was to determine the oxidation number of the elements in bold. So first example here, we have ClO2, ClO4 minus, and SO4 2 minus. In the first 2 cases, we are looking for the oxidation number of chlorine. And the third case, we are looking for the oxidation number of sulfur. Okay, so let me solve this exercise, and then you can check if you got it right, or if we need to go back and review something. Okay, so let me switch screens here. Okay, awesome. So let's start with the first one, ClO2. So first thing that you always have to pay attention is if the compound is charged or neutral. In the case of ClO2, this is a neutral compound because there is no number on the right upper corner. So I'm just going to write here 0 just to make it easier, but you need to know that there is no charge over there. If the net charge of the compound is 0, that means the sum of the oxidation numbers for all the atoms in the structure must be equals to 0. We know that oxygen usually has oxidation number -2. So let's write here -2 is the oxidation number of oxygen. However, we have two atoms of oxygen in the structure, which means we have to multiply by 2. Okay, always multiply the oxidation number by the number of atoms in the structure. The oxidation number of the chlorine is what we are looking for, so I'm going to call it X. And X is going to be multiplied by 1 because we just have one atom of chlorine in this structure. Therefore, the only possible value for X is +4. Or you can also write 4 plus. Okay, so doesn't make any difference here. So that's the oxidation number for chlorine in the compound ClO2. So that means when chlorine is bonded to two oxygens, chlorine virtually lost 4 electrons. Okay? The meaning of that is that the electrons are closer to the oxygen than the chlorine. The second example, now there is a slight difference here in this compound. So for ClO4, now attention here, because now we have a net charge for the compound, and the net charge is 1 minus. So the result of having a net charge of -1 is that the sum of the oxidation numbers has to be equals to -1. Okay, so always pay attention to that. Okay, and then we do basically the same thing that we have been doing. Oxidation state of the oxygen is -2. Attention here, because we have 4 atoms of oxygen, therefore we need to multiply by 4. And the oxidation number of chlorine is what we are looking for. Therefore, the only possible value for X that satisfies this equation is +7. Or you can also write 7 plus. Always pay attention to the net charge of the compound. And finally, the last example here, SO4 or sulfate ion. Now for SO4, we have a net charge of 2 minus. That means the sum of the oxidation numbers for all the atoms in the structure of the sulfate ion has to be equals to -2. And then again, we basically do the same thing that we did before. The oxidation number of oxygen is usually -2. We need to multiply the oxidation number by the number of atoms of the element in the structure. In this case, we have 4 and times 4. And what we are looking for is the oxidation number of sulfur. I'm going to call X. Therefore, the only value that satisfies this equation is +6, or you can also write 6 plus. And that's how you determine the oxidation numbers of all the elements in the structure of a molecule or an ion, okay? So just follow the rules, and there is always one element that we need to find the oxidation number, and that's how you do it. Remember, a positive oxidation number means that the element in this specific compound lost electrons. On the other hand, a negative oxidation number means that the element gained electrons in the compound. Okay, so very good. Okay, let me switch screens again. Okay, awesome. So now to finish up redox, I will show you how to use the oxidation number first to classify when an oxidation or reduction is happening. Second, to identify an oxidizing and reducing agent. And third, to balance any sort of chemical reaction using the variation of the oxidation numbers. So let's see here as an example this reaction that I'm showing here. So the goal is to balance the reaction, but not using trial and error, but variation or change in the oxidation numbers. For this reaction, we have calcium phosphate reacting with silicon dioxide and carbon. And the products are going to be P4, which is phosphorus, calcium silicate, and carbon monoxide. Okay, so what I want from you is to determine the oxidation numbers of all the elements here in the equation. Okay, so for example, for the first compound, I need you to determine the oxidation number of calcium, phosphorus, and oxygen. For the second compound, silicon and oxygen, and so on until carbon monoxide. Okay, so I'm going to give you about 3 minutes, and then we will do together, and then we are going to classify when an oxidation or reduction is happening, oxidizing and reducing agents, and I will show you how to balance the reaction using the variation of the oxidation numbers. Okay, so a quick 3 minutes, and then we will do together. Okay, so let's do this together. Then you can see if you got it right or if not. Okay, so the first goal here is to determine the oxidation number for each element in the equation. So let's start with calcium phosphate. So just to make things a little bit simpler, I'm going to write calcium phosphate like that, Ca3P2O8. So the only thing I did here was to multiply the index outside of the parentheses by the index inside the parentheses, okay? So that will give us the number of atoms in the structure. This is a neutral compound, therefore the sum of the oxidation numbers is 0. And we have here calcium, phosphorus, and oxygen. If we go back to the rules, rule number 6 states that elements from the group 2, when combined, have oxidation number 2 plus. So that's is going to be our starting point. So therefore, we know that calcium has an oxidation number of +2. Attention here because we have 3 atoms of calcium in the structure. Therefore, we must multiply by 3. We have here our friend oxygen. So always refer back to the rules if you don't remember. Rule number 4, the oxidation number of oxygen is usually 2 minus. The exception is when we have peroxide compounds, which is not the case here. Okay, so therefore we know that oxygen is 2 minus or minus 2, and again we have 8 atoms of oxygen in the structure. Therefore, we must multiply the oxidation number by 8 in this case. And what we are going to look for here is the oxidation number of phosphorus. So I'm going to call it X. Careful here because we have 2 atoms of phosphorus in the structure. Therefore, we must multiply by 2. Okay, and the sum of all the oxidation numbers, they have to be 0. Therefore, the oxidation number for phosphorus is +5 in this structure. So therefore, what I'm going to do here is to write the oxidation number for each element on top of the formula. Calcium, we found 2 plus. Phosphorus, we found 5 plus for each phosphorus. And oxygen, we know that is 2 minus for each oxygen.
Excuse me, George.
Yes.
How did you know that you were looking for the phosphorus specifically and to therefore use it as the X?
Yes, that's a good question. Sorry about that. If you go back to the rules, phosphorus is not in any of the rules. So that's the clue that you need to find the phosphorus. Okay?
Yes, thank you.
Yes. Okay. Okay, so let's just refer back to the rules. So basically, between the rules 3 and 6, that's where we are going to look for elements. So again, hydrogen is 1 plus, oxygen 2 minus, fluorine always 1 minus, group 1, 1 plus, and group 2, 2 plus. If the element is not within the rules, then we need to find it. Okay, that's how you will know what to find and what you need to know. Okay, moving on to the next compound. Here we have silicon dioxide. And again here, in the rules we have oxygen, but silicon is not in any of the rules. Therefore, it means the oxidation number for this element will change according to the compound, which means we have to determine the oxidation number. Silicon dioxide is neutral. Therefore, the sum of the oxidation numbers has to be zero. Oxygen is -2. We have 2 atoms of oxygen in the structure. Therefore, we need to multiply by 2. And silicon is what we are looking for. Therefore, the only possible oxidation number for silicon in this compound is +4. So again, I'm going to write the oxidation number for each element on top of the molecule. Oxygen, we know that it is 2 minus, and silicon, in this case, we determined 4 plus. Okay, careful with the next compound is carbon by itself. So let's go back to the rules. see here rule number 1. Each atom in a pure element has an oxidation number of 0. Okay, so if the compound is formed by only one kind of element, that means the oxidation number of this element has to be 0, unless there is a charge outside. So here we have carbon by itself, no charge outside of the compound, which means the oxidation number for carbon is 0. And we can use the same rule for the next compound, P4. So that's phosphorus bonded to phosphorus. Again, is a compound formed by only one element, no charge on the outside, which means the oxidation number for phosphorus has to be 0 as well. Okay, next compound, we have here a calcium silicate. And then again, calcium is from group 2. Therefore, we know that the oxidation number is going to be +2. Oxygen oxidation number is going to be 2-, unless we have a peroxide, which is not the case. And silicon is the element that does not have a fixed value for the oxidation number, which means we have to determine in each compound that this element is present. This is a neutral molecule. Therefore, the sum of the oxidation numbers has to be 0. Here, calcium is +2. Oxygen is -2. We have 3 atoms of oxygen, therefore we need to multiply by 3. And silicon is the one that we are looking for. Therefore, the only value possible here to satisfy the equation is +4. And I'm going to write the oxidation number for each element on top of the structure. Calcium 2+, silicon 4+, oxygen 2-. And finally, the last molecule, carbon monoxide. Again, this is a neutral molecule, which means the sum of the oxidation numbers is 0. Oxygen oxidation number is -2, and carbon is the one that we need to find, because carbon may change the oxidation number when bonded to different elements. Therefore, the oxidation number for carbon in the carbon monoxide is +2. Okay, and let me write here 2+ and 2 minus. Okay, now that we determined the oxidation number for each element in each compound in the chemical reaction, now I want you to look at all the oxidation numbers and try to note any sort of change that happened. So if we start looking at calcium, the oxidation number started at 2 plus, and at the end, right here, we have 2 plus, okay? So no change for calcium. Oxygen started with 2 minus and ended at 2 minus, independent of the compound that we are looking for. Silicon started at 4 plus and ended at 4 plus as well. However, when you look at phosphorus, the oxidation number initially for the atom was 5 plus. However, at the end of the reaction, look what happened with the oxidation number of phosphorus. It became 0, okay? So therefore, we have a change from 5 plus all the way to 0. And if we look at carbon, started from 0 and at the end of the reaction moved to 2 plus, okay? So it is the opposite thing that happened with carbon relative to phosphorus. Started from 0 and increased to 2 plus, while phosphorus started from 5 plus and decreased to 0. So therefore, now it's a good point to introduce the concepts of oxidation and reduction. So I'm going to write here again the oxidation numbers for only the elements that are changing during the reaction. So we have here phosphorus going from 5 plus all the way down to 0. Every time that the oxidation number decreases, we call this process reduction. Okay? Any reaction will have an element that reduces and another element that do the opposite. Okay? So therefore, the element that's reducing in this equation is phosphorus. Reduction means electrons were gained. On the other hand, carbon started with an oxidation number of 0, and at the end had an oxidation number of 2 plus or plus 2. Therefore, carbon increased the oxidation number during the reaction, which means a loss of electrons. And this process, when the oxidation number increases, is called oxidation. The element that has its oxidation number increased, we are going to call that this element oxidized. And in this particular reaction, the element that oxidized is carbon. Okay, so when I'm looking at oxidation and reduction, I'm just looking at the atom that either gained electron, reduction, or lost electron, oxidation. Now attention here. Let's now tackle the concepts of oxidizing agent and reducing agent. Be very careful with those concepts when compared to simple oxidation and reduction. Oxidizing agent is the compound that causes the oxidation, which means this is the compound that got reduced. And reducing agent is the compound that causes reduction. This is the compound that got oxidized. Okay, so oxidizing agent is the opposite of reduction, and reducing agent is basically the opposite of oxidation. So let's classify in this reaction the oxidizing agent. And here for oxidizing agent, we are going to look at the compound that got reduced. Okay, so now for the agents, we are looking at the whole molecule. So let's look here who got reduced. Who got reduced is phosphorus. Therefore, calcium phosphate is going to be our oxidizing agent. You may imagine the oxidizing agent as the molecule that causes someone to oxidize. Okay. And then reducing agent, we are going to look at the opposite. Reducing agent, we are going to look at the compound that got oxidized. Okay. So again, for agents, we look at the whole molecule that suffered oxidation. And the compound that oxidized, sorry, the element is carbon. Therefore, the reducing agent is going to be the whole molecule that has carbon in the reagent site. And in this case, is simply carbon right here. Okay, so carbon by itself. Imagine the reducing agent as the compound that had to lose electrons to reduce someone else. Okay.
Excuse me, George.
Yes.
So for oxidizing agent, are you always looking at the left side of the equation, and then reducing agent, you're looking at the reagent side?
Yes, always for oxidizing agent and reducing agent, you look at the left side of the equation. Okay.
Okay.
Mhm. And then be very careful here. When you are just looking for oxidation and reduction, you are looking at only the element. Okay. An agent, you look at the whole compound that contains the element that reduced or oxidized. That's why, in this case, phosphorus is the element that reduced. However, the oxidizing agent is calcium phosphate, because this is the compound that contains the phosphorus. And always look at the left side because that's where everything started. If someone reduced, someone has to oxidize. Okay? Reduction means that electrons were gained, which means someone has to lose electrons for the process to move to the right side. Therefore, in a chemical reaction, we cannot create or destroy atoms, and also we cannot create or destroy electrons. It's always going to be a movement of electrons. And chemistry is basically based on movement of electrons. Someone will reduce and someone will oxidize. And we have to keep the balance. And at the end, we balance a chemical reaction to keep the atom balance and also the electron balance. So now let me introduce you how to do the balancing of the reaction, just looking at the change in the oxidation numbers. So I'm going to calculate a factor called delta. So delta means how many electrons were gained or lost. So let's start with phosphorus. Delta is going to be the change in oxidation number, and that's an absolute value. Phosphorus started from 5 plus and moved all the way down to 0. Therefore, the absolute change was 5. Okay. From 5 plus to 0, we have to gain 5 electrons. And you are going to multiply this factor by the number of atoms in the reagent side. Phosphorus, there are 2 atoms of phosphorus in the unbalanced reaction on the left side. Therefore, we are going to multiply this by 10. And this factor delta is going to be 10. And I'm going to do the same thing for the oxidation leg of the equation. So again, here we are going to determine a parameter called delta. Delta will tell us the absolute change in the oxidation number. Carbon started from 0 and went to 2 plus. Therefore, the change is 2. And we have always to multiply by the number of atoms on the reagent side in the unbalanced reaction. For carbon, we just have 1. Therefore, 2 times 1 is 2. And now here is going to be very simple. The delta from the oxidation leg of the equation is going to be the stoichiometric factor, the stoichiometric coefficient for the element that reduced. So therefore, the 2 here will move as the stoichiometric coefficient for the compound that reduced. And we are going to do the opposite with the delta from the reduction leg of the equation. So the number 10 is going to be the stoichiometric coefficient for the element that oxidized. Okay, so we just switched the deltas. The delta for the reduction becomes the stoichiometric coefficient for the element that oxidized, and vice versa. And those are going to be the stoichiometric coefficients that you will work with to balance the whole reaction. So we know here that we have to have 10 carbons on the left side. Therefore, we simply balance the CO2 with 10, because that's the only spot that has carbon. Another element that we can balance is the calcium, 2 times 3. We have 6 atoms of calcium on the left side. The only place to balance out calcium is right here. So therefore, we are going to balance calcium. Now we have 6 atoms of silicon on the right side. The only place to balance out silicon is silicon dioxide. So we add here the stoichiometric coefficient of 6. And what is left is phosphorus. So we have 2 times 2, 4 atoms of phosphorus on the left side. Therefore, we must have 4 on the right side, which means a stoichiometric coefficient of 1. And that's how you can use the change in the oxidation numbers to balance or to start balancing any chemical equation, okay? So using this strategy, you should be able to balance any kind of reaction from the simplest ones to the most complex equations, okay? So what I want you to keep in mind is to identify when an element oxidizes and when an element reduces, and understand the difference between oxidizing agent and reducing agent, okay? Just be very careful with those concepts. Okay, and with that being said, this is the end for today, and I will see you tomorrow. Have a good week.
Thank you, Professor.
Have a good rest of your day.
Bye-bye.
Thank you. Have a nice day.
Thank you. Bye.